Hey there, science fans. Today, we're diving into sequential logic circuits. These circuits can remember things. Imagine circuits that store information like your brain. That's sequential logic. At the heart are flip-flops and latches. These components act like switches that remember their state. Think of a light switch. When you flip it on, the light stays on. That's what a flip-flop does. Flip-flops and latches are the building blocks of complex circuits. They help us create circuits that count, store data, and control events. Pretty cool, huh? Stay tuned. Welcome back, circuit explorers. Now that we know about flip-flops, let's meet the different types. It's like a family reunion, but with electronic components. First up, we have the SR flip-flop. SR stands for set reset. It's like a light switch with two buttons. One to turn it on, set, and one to turn it off, reset. Next, we have the JK flip-flop. This one's a bit more versatile. It has two inputs that can be used to set, reset, or even toggle the output. Think of it like a light switch that can be controlled by two different people. Then there's the D flip-flop, short for data flip-flop. This one's a bit simpler. It has one input and simply stores whatever value is on that input. Imagine a notepad where you can write down a number and it remembers it for you. Finally, we have the T flip-flop or toggle flip-flop. This one's a bit unique because it can change its output state every time it receives a specific signal. Think of it like a light switch that changes from on to off and off to on every time you press the button. Each type of flip-flop has its own special abilities, making them useful for different applications. Isn't it amazing how these tiny components can be so diverse? Hey there, memory masters. Remember latches? They're like flip-flops, but with a slightly different way of remembering information. We'll start with the SR latch, similar to the SR flip-flop. It has two inputs, set and reset. The key difference is that the latch's output changes immediately when its inputs change. It's like a really responsive light switch that turns on or off as soon as you touch the button. Next up is the D latch. Like the D flip-flop, it has one input and remembers whatever value is on that input. However, the D latch's output changes immediately when the input changes, just like the SR latch. Latches are often used in situations where we need to quickly capture and hold information. They're like the quick reflexes of the digital world. Section 4. Counting on counters and registering results. Welcome back, digital dynamos. Let's see how flip-flops help us build amazing things like counters and registers. Counters are circuits that, count. They use flip-flops to keep track of the number of times something happens, like button presses or clock pulses. Imagine a counter keeping track of how many times you jump up and down. That's a counter in action. Registers, on the other hand, are like tiny memory banks. They use flip-flops to store multiple bits of information, like a digital notepad for your circuits. Think of a register as a group of friends, each holding onto a piece of a secret message. To build a counter, we connect flip-flops in a special way so that their outputs represent a binary number. And guess what? With each clock pulse, the counter increases its value, just like counting. Counters and registers are essential for many digital systems, from clocks and timers to computers and smartphones. They're the backbone of digital counting and data storage. Section 5, State Machines and Mapping Out Circuit Behavior. Greetings, circuit champions. In our final section, we'll explore state machines, powerful tools that describe the behavior of sequential circuits. Imagine a board game where you move from one square to another based on dice rolls. State machines are similar. They use states to represent the different possible conditions of a circuit and transitions to show how the circuit moves between those states. There are two main types of state machines, Moore machines and Mealy machines. Moore machines' outputs depend only on their current state, like how your position on the board game depends on the last dice roll. Mealy machines, on the other hand, have outputs that depend on both the current state and the inputs. Imagine your next move depending not only on your current square, but also on a special card you draw. State machines are like roadmaps for our circuits, helping us design and understand their behavior. They're used in everything from traffic lights and washing machines to complex computer systems. So there you have it. An exciting journey through the world of sequential logic circuits. From flip-flops and latches to counters, registers, and state machines, we've seen how these amazing components form the foundation of our digital world. Keep exploring, keep questioning, and keep the spirit of science alive.